hiccups that we had with these lockdown browsers working for or working with or the operate against the operating system. Google Chromebooks have a different operating system from Windows, Mac, and iOS, which iOS is an iPad operating system for iPad and iPhone. So three different devices that support lockdown browser and monitor, I believe. But Chromebook just does its own thing. So in the future, I think hopefully for exam two, this is what I have in mind: two separate links, two separate passwords. One for the people with a lockdown browser, one for people with Chromebooks. So there'll be two. When you go to your grade book, you'll see two different columns. Obviously, one column will say exam two for people with Chromebooks and without Chromebooks. So don't get confused if there's two different columns, because I'm just going to record the information from both columns and then combine them into one. So that was the best thing I can think of to culminate, the few portion that has Chromebooks and don't have Chromebooks. Because once I turn off lockdown browser and turn on lockdown browser and start turning it off and on, once students have started the exam, it goes out of whack, and it was working for some people, it was working with others. Even yesterday, we Zoomed trying to get the exam started, but someone emailed me like, never mind, I figured it out. But I still Zoomed with the others how to figure it out, but it was just not working with me. So that's what I have in mind. That seems like it would be the simplest way to avoid any hiccups, any stress, worries about, am I going to finish on time or can I access it and within enough time to interpret the material and execute what they're asking me or asking me to solve or find. So I think next for exam two, we'll have two links, have two separate links, so similar to this time, but way in advance. So for this next coming exam, my personal opinion, 6.5 and 6.6 are going to be very easy compared to 7. Now, I mean it when I say very easy, because 7 involves trigonometric identities. The sine squared plus cosine squared is equal to 1. I think at the end of 6.3, we talked about sine squared plus cosine squared is equal to 1. That's known as Pythagoras' identity. I know you've worked with Pythagoras theorem pretty much all your life, right, with right triangles. So now we'll be extending that idea to Pythagoras' identity. Again, sine squared plus cosine squared is equal to 1. That was one of the main things we saw at the end of 6.3. Not saying that's the main thing in chapter 7. It's just that we're going to have to use a lot of manipulations of trig identities, such as our reciprocal identities and the Pythagorean identities. All right. So now that we played with some right triangles, we'll play with some non-right triangles. The first of this first half of chapter 6 may have been very similar if you've already taken geometry course. Not too sure how far they go in your geometry course, so nowadays in the curriculum. But here we'll look at law of sines and law of cosines. So here we'll look at our special triangles: side, angle, side. I'm sure that rings a bell. So depending on the triangle we have, the information is presented. Because there's 6 parts of a triangle, like we mentioned earlier, 3 angles, 3 sides. So depending on what's given, we have to use either the law of sines and the law of cosines. So law of sines, they give us 2K, pretty much how to use the law of sines, the equations, and then we'll end it with the ambiguous case if we have enough time. All right. Law of cosines is a little bit shorter. The law of sines. So let's take a look. And trigonometric functions, or the trigonometric function, can also be used to solve oblique triangles. That is triangles with no right angles. So far, 6.1, 2, 3, everything's a right angle. Triangle is a right angle. Okay. For instance, if we were given two angles, all right, as you can clearly see, we're given from the bottom these little black lines here. Let's draw little curves right here. We have our that's red. Not really emphasize that well. Right here are our two angles, right? For instance, if we're given those two angles and included side, this bold side of the triangle, then it's clear that only one triangle can be formed. So we see that in the figure below. Next slide. Similarly, they say if two sides and the included angle, so now we have a side angle side compared to this one was angle side angle or side angle angle, either or counts. So I like to see this one as angle side angle. But it's they're abbreviated, right? So it's so hard, or it's so easy just to swap all the S for an A and A for an S. So angle side angle is the first case that we saw. This second case is similar. Two sides and the included angle are known. It forms this triangle, and here we get side angle side angle side, right? So, but if we know all three angles and no sides, we cannot uniquely determine the triangle because many triangles can have the same three angles. So we need to know at least a side, at least a side. If we know all three angles, great. We know all the sums should equal 180. But knowing the three angles does not tell us anything about figuring out a side. So we need at least one side of the triangle. All right, so here we had an angle, side angle. We had two angles and we had at least a side. Here we have two sides and we have an angle. So that gives you an idea, a perspective, what you need before you can start. So here we have our four different cases. So general, a triangle is determined by three of its six parts. The angles, three sides. Along at least one of the three parts is a side, we can solve for the rest of the triangle. So again, what I was mentioning earlier, hopefully you notice that at least a side needs to be given. So the possibilities that we see are illustrated in the figure below. Here we have angle, side angle, side angle, side angle side, and side. Right. So this one's kind of easy to remember, right? SSS, side. C and D will be used for law of cosines. We'll be using A and B. So let's focus on the first two that we saw: angle, side, angle, and side. I think it was side, angle, side. I think we look at C. I think side, angle, side, right? I believe so, right? So maybe they're not restricting these two to law of sine. So I was jumping the gun. So we're gonna have two of them. The two cases that we'll use for law of sines. The other two cases we'll use for law of cosines. So in general, again, triangle is determined by three of its six parts, angles and sides. So as long as at least one of the sides is given, we can solve for it. At least one of these three parts is a side. We have these possibilities here. Case one was angle, side, angle. Case two was side, angle. Case three was side, angle, side, and then side. So yes, that was correct. Case one and two were for law of sines. Case 3 and 4 were law of cosines. So we'll focus on case 1 and 2, which was angle, side, angle, and side, angle. Side, angle. Okay, side, angle. This one was side angle. Okay, side, angle, side. This one was cosine. So here they just gave us two examples, and then here we're already broken down. Okay, the first two are for law of sines, second two law of cosines. Now you're probably wondering, what is the formula? How do I use the formula? So here we get to our formula with sine, law of sine. So it may look a little bit weird. I know you do see two equal signs. So the law of sine says that in any triangle, the lengths of the sides are proportional. That's the key word, proportional to the sides of the corresponding opposite angles, right? Proportional to the signs of the corresponding angles. So I know this formula looks confusing, but here given that we have a triangle ABC, they said the law of sines is the following. So here we have sine, capital. Notice capital A and little a. They mean two different things. So sorry, I meant to put up my PowerPoint. All right. So notice capital A, capital B, little c, and so on. So capital letters and little letters are two different things. So here we're going to denote the large letter, capital A, B, C. Those will be for angles A, B, and C. Little, lowercase a, B, C. Lowercase is going to be for the sides. Side A, side B, side C. So keep that in mind. The large letters are for the angles. The small letters are for the sides. All right. Now again, you're probably wondering, well, there's two equal signs. How do I use this? So depending on the triangle you're working with, depending on what was given, you set up any two fractions to be equal to each other because they're proportional. So let's say the triangle you're working with only gave you information about A and B. So you had angle A, angle B, side A, but you're missing a side B, for example. Then you wouldn't worry about this part. You set these two to equal to each other. So that's the idea here. So depending on what is given, you set them to equal to each other. So let's say they gave us information about A and C. So then you just set up sine of A over little a is equal to sine of C over little c. So depending on what is given, you just choose any two fractions to equal each other. So that's pretty much what this. I know the formula does not explain itself, but since they're proportional to each other, you can grab any two pairs and set them to equal each other, and then solve for what's missing. And then grab any other pair that let's say you're trying to solve for all 6 parts of the triangle. Then you grab another pair, and then solve for what's missing. So let's see if we can have an example coming up. See if we can use that. All right. Here we get an example. Here we get like I said, a little application problem. So it says a satellite orbiting the Earth, passing directly overhead at observation stations in Phoenix and at Los Angeles at 340 miles apart. So we know these cities are 340 miles apart. At an instant, when a satellite is between these two stations, all right, so at an instant when the satellite is, so try to paint a picture in your head that about, the distance between these two cities. And at an instant when the satellite is between these two stations, its angle of elevation is simultaneously observed to be 60 degrees at Phoenix, 75 degrees in Los Angeles. Now they want to figure out how far is that satellite from LA. All right, seems pretty interesting, right? Well, something we would want to know, right? Some scientists, right? They would want to know that information. All right, so first thing first, they went ahead and helped us out, but I think we could have painted that picture in our head. We can move this to the side. Move this in the side. So let me make the picture a little bit bigger. All right. So I could try to draw this myself as well, right? So then try to draw, right? This would be LA is more west, right? I believe that's in California. Phoenix is in Arizona. And then have some satellite in space, right? So this is me trying to draw the diagram, assuming I didn't know the figure. Then they say the distance between these two cities is 340 miles. And then they say the angle when observed is 75 degrees here at LA, and I think they said 60 degrees in Phoenix. All right. So, my picture's better than theirs, obviously, right? So we drew a little example, and we'll call this triangle A, triangle B, C. And notice how I use capital letters. So every time you know an angle or a side, so angles are always capitalized. The side of that angle is always across it. So this would be little a, this would be little b, and across angle C, which we don't know, we could solve for angle C we liked, right? And this side would be little c, little c, little c. So let me change that color. Let me put that in red. So this would be side A. This would be side B, and then on the bottom, side C was given to be 340 miles. All right, perfect. All right, let me bring the picture closer to this one, right? So you have a better figure, right? My figure's just as good though. All right. So we know the distance between the two cities is 340. We know angles to be 75 and 60 degrees respectively. Looks like we're trying to solve for little b, because they wanted to find the distance between Los Angeles and the satellite. So we can figure out the missing angle. So since the sum of the angles of any triangle is 180 degrees, let's find out what angle C is. Angle C happens to be just 180 minus the sum of the other two angles. So, I gave myself some space, but we can do this here. All right, so 180 is gonna, angle C is gonna be 180 degrees minus 75 degrees plus 60 degrees, which equals 45 degrees. 45 degrees. All right. And the reason why I did that is because I needed to find that missing angle, which was 45 degrees. 45 degrees. And the reason why I wanted to use, or I wanted angle C, is because I need to use the proportion sine, because we're solving, we want to find little b, right? The whole point is to find little b, right? What is little b equal to? So they mentioned we can't solve for anything without knowing a side. So at least we know one of the sides was LA to Phoenix, and that happens to be side C. So we have to use this one because we know little c. We need to know one of the sides in order to solve this triangle. So that's why I went ahead and set up sine B over little b is equal to sine C over little c. So because I know angle B, I know angle C, I know little c, and then there's only one part of the formula that's missing. When you have all but one parts of a formula missing, you can solve for this. So this is just law of sines right there. And let's go ahead and solve for this. So we'll do that on the next page. That's what I gave us some space for. I'll set up the formula again. Sine capital B over little b equal to sine of capital C over little c. All right, so let's get down. Angle B, I think, was 60 degrees. Angle C, we got to be 45. And then they gave us side C, which the miles, 340 miles. 340 miles. Okay, so let's just plug in and then solve for what we need to, which is little b. All right, since this is an application problem and we're dealing with degrees, sine of 60 degrees, sine of 45 degrees, you're going to need to set your calculator into degree mode, or if you simply have your unit circle, you would just look at sine of degrees and look at the respective value for that. So let's plug everything up here. Sine of 60 degrees. I don't know little b. That's what we're solving. But we do know sine of angle C. Angle C happens to be 45 degrees. over little c, which is 340 miles. All right. To solve, we need to do a little manipulation. So a little bit of algebra. I need to solve for b. I need to solve for b. Um, don't want to make it too tedious as we do the algebra. So again, little b is trapped underneath a sine of 60 degrees. So it's being divided by little b. So we multiply by b. We multiply by b on both sides, right? So now we have sine of 60 degrees over b times sine of 45 degrees. So this might be the hardest part, actually doing a little bit of algebra. So we're not even doing pre-cal right now. We're doing algebra. The pre-cal part was the sine of b over little b, sine of c over little c. That was the pre-cal part. This is just simply just algebra. Again, we're solving for little b. Let's go ahead and multiply by 340. We're trying to isolate little b. So this is just algebra. So cancel. We're gonna be left with b times sine of 45. So I probably need to make a new slide, which I have here. B times sine of 45 degrees is equal to, all right, what's left over? 340. This looks like sim, right? This is sine. 340 times sine 60. 340 sine 60, sine of 60 degrees. And then we just need to divide by sine of 45. We're almost there. There you go. This is canceling out. And then make sure to have a trusty calculator set in degree mode, because this part, we'll take, we can't get an exact answer without using a calculator. We do know the value of sine of 60 degrees and sine of 45 degrees. Those are special angles that we have on our unit circle. But since they want us to find the actual distance, I don't think a square root's gonna, give us an idea. If we have a square root of some number that we're not used to, it's nothing to give us an idea of how many miles that satellite is from LA. Now, it took a little bit of work here, so now we just got to plug in 340 times sine of 60 degrees divided by sine of 45. Let's round to let's round to the nearest whole number. So little b. Anybody can help me out. I know it took a little bit of work, but now we're just left with to plug in what we have before our approximation line. So I want to see if anybody got the exact miles rounded to the nearest whole mile. So you just need to plug this in. Did anybody get something within the 300 to 400? 416, awesome there. I wanted to throw you guys off by saying a different number. 416, so awesome, easy. So approximately the distance, right, of the satellite, from LA is approximately 460 miles. You need to wrap it up, but I wanted to wrap it up. It doesn't really look that pretty, but we found what we're looking for, and that was 460 miles right there. So that's why I say these problems are not difficult in the sense if you just plug into your calculator, but it does involve a little bit of multiplying when you need to solve for what you need to solve for. So other than that, I think this one was a little straightforward. So depending on what is given, you need to you need to choose whatever two fractions from here. So this is an easy formula to remember. It's just basically sine of a over sine of any letter you want to choose over the little letter of that if you choose. Because we don't have to use ABC. We can use triangle XYZ. We can use any three letters, and they don't have to be consecutively back to back to back. It'll be a little bit weird, but traditionally we do consecutive letters, ABC or XYZ, namely ABC. All right, so that wasn't too hard. First one was a little easy. This brings us to the ambiguous case. So let's see what we have here. So the first example we saw, a unique triangle was determined by the information given. This is always the case for, this is always true for case one, angle, side, angle. That's not even what we work with. Here we do with angle. So they're talking about angle, side angle. Oh yeah, we did do an angle, side angle, right? Angle, side angle. Yeah, yes, we did. So the first example we did was an angle, side angle. Yes, we had the two angles. We had the angles 1675. So this is always true for case one, the angle, side angle, the one we did. But in case two, what is case two? Case two, all right. Case two, what is case two? Case two happens to be side angle, all right. Side angle. All right, what are they trying to tell us about case two? Okay, looks like case two is dealing with the ambiguous case. So, so the first example gives a unique triangle. Now, this is always true for the case of for case one, but in case two, side angle, there may be two triangles, one triangle, or no triangle with the given properties. So the first case, uniquely determined one triangle, and now they're saying side angle, they may be two, one, or no triangles given with the properties. For this reason, case two is sometimes called the ambiguous case. So if you do read online about the ambiguous case, they're more likely talking about this case of the law of sines. And they're going to demonstrate, they go ahead and demonstrate here the examples of having one, two, or no triangles. So to see why this is so, they show us in a figure down below with 4 different pictures. The possibilities when the angle A and sides A and B are given. So here we have, we know 2 sides and an angle. So side A and B and angle A. So angle A is given in all of these and side A and B. So in the first case, A, it says no solution is possible since side A is too short to complete the triangle. That one's a little bit easy, a little straightforward, right? It doesn't even form a triangle. Side A is just too short. Yes, we were given 2 sides, side A, B, and an angle, but since this does not even form a triangle, there's nothing we can do here. Right. So in part A, no solution is possible since side A is too short to complete the triangle. In side B, or in part B, example B, the solution is a right triangle. So a right triangle is pretty easy. We just need to use Pythagorean theorem, right? Now it says in part C, 2 solutions are possible. Notice that line segment that's broken down right here. That line segment right there. Right? This arrowhead, a line segment there. Now I think we worked with one with a perpendicular bisector. That one strictly, it was an equilateral triangle. This one, it went perfectly down in the middle. Those were those special cases I think we looked at. So that bisector does not have to be perfectly straight down the middle, as we can see in case C. Looks like it goes off at an angle and it forms actually 3 triangles, right? There's 1, 2, and then the whole triangle itself, right? But they're talking about in case C or part C, 2 solutions are possible because we have 2. Once we know the 2 triangles, we can figure out the third triangle, the whole triangle itself. So In case C, we see the two triangles there. Two solutions are possible. And in part D, there's a unique triangle with the given property. So um, quite interesting. A was a little bit silly, right? But the other ones are pretty interesting to look at. Okay. Okay, it says we illustrate the possibilities of case two in the next example. So case two again was side angle, side angle. So we'll see that in an example that's coming up right now. Right there. Okay, so right away I see a side. So I see a side, I see another side, and I see a angle. Right. So side, angle. That looks like case two. So it is case two. Okay. Solve the triangle. Solve triangle ABC, where angle A is 45 degrees. Little a is 7√2. So across angle A is little a. So we know that side. 7 times square root 2. Again, it's not really, I don't know what that is in inches, right? You would have to multiply it, but we'll roll with it. We also know side B, right? Because this is angle B. We don't know angle B, but we know side B. We know side B. We know little b. All right. So let's jot down what we have. We have angle A. We have angle A. We have little a. So angle A is 45 degrees. We have little a, which happens to be 7 square root 2, and then little b, who happens to be 7. All right. Based on the information given, okay, what are we looking for? Right, we could solve for everything, but what are they asking us specifically? All right, we first sketch our triangle with the information. So we went ahead, or was sketched already, but we went ahead and jotted down what was given. Angle A and little b. We did that in blue. So and then from there you can sketch our triangle. So here we sketched a triangle from the information that was provided above. Our sketch is necessarily tentative since we do not know the other angles. So you can draw it freehand. You don't have to get a protractor and exactly have a 45 degrees. So that's fine. Nevertheless, we can see the possibilities. So here we do a little sketch: triangle A, B, C. It's not too hard. Again, it's going to be freehand. So doesn't have to be perfect, right? Our sketch is necessary tentative since we don't know the other angles. So just freehand it. Right? 7√2 and 7. So it's not too difficult to come up with these triangles. So maybe we'll sketch it roughly pretty quick too. Again, this is little a, little b, and this would be little c. All right. So which two proportions? So based on what's given here, we have angle A, and little b. Based on this, which two are we going to pick for this particular problem? Since I have angle A, little a, and angle B, which two fractions am I going to pick? The first two? We don't have any information about C, do we? Do we know anything about angle C and little c? The first two, right? So if you want, I don't like to scratch it out. I mean, I like to put my finger over it just to cover it. Yes, we're going to use sine of A because we could have used sine C if they gave us information about angle C and little c. Unfortunately, they gave us information about A and B. So we're going to pick those two fractions. Awesome. That's what I wanted to illustrate, that hopefully this formula is not confusing. You just pick any two fractions to equal each other based on what was given. So they gave us information about A and B, and they left us hanging. They left us hanging in the sense that we need to figure out angle B. So they're making us do a little bit of work here. So first, Let's solve for angle B. All right, let's solve for angle B. Here's the formula. If you don't like messing with algebra, because if you just know this law of sines, you can manipulate it with algebra and solve for whatever you want. So they went ahead and those of you who answered, thank you. If you looked ahead, you probably be like, "Oh, it's just A and B both." So they give us a little breakdown. We set up the proportion of the A and B equal to each other, and then they went ahead and solved for sine of capital B. All right. So if you want to write this down in your book, that would be the formula to solve for sine of angle B. All right. But again, they just did one move. They just multiplied by B. Cancel, cancel. B times sine A over little a. So that's all I did, multiply by little b. Now that we have our formula, sine B is equal to B sine capital A over little a, let's just plug everything in, right? Let me go ahead and rewrite what I have. The angle A was 45. Little a was 7 root 2, and little b was 7. All right, let's just plug this in. I don't know sine of b yet, right? So this is sine of b. Little b was 7. Sine of capital A, sine of 45 degrees. And then we have little a happened to be 7 root 2. All right. Make a little bit of space by making a new slide. If you want to cancel a little bit out before you plug into your calculator, that's fine. You notice these 7s will cancel out. All right, and we're left with sine B, sine B, capital B, sine 45 over square root 2, sine 45, sine of 45 degrees over and square root 2. Square root 2. All right. So far, so good. Everything's been great. Everything's been great. We can actually plug this in. What does this give us? One half, 0.5, right? 0.5 or one half. We can actually do this by hand. I don't know how to get rid of this thing right here. Can't get rid of it. All right. Yeah, it is one half. We're just moving on, working a little bit. Remember, sine of 45 degrees is square root 2 over 2. This is being divided by square root 2. So sine of 45 degrees is always square root 2 over 2. It's always, right, from the unit circle. So keep change flip. Keep if you're dividing, right, some fraction by another fraction, keep the first fraction the same. Change the division to multiplication and flip the second number, which is going to be square root 2 over 1, which becomes 1 over square root 2. Notice my square root 2's cancel out, and we're just left with 1/2. So this is if you did it by hand. All right, so here we get, so we're still left, we're still stuck, right? We still don't know what sine of B is. We still don't know what sine of B is, but we are down to sine of B is equal to 1/2, which was provided by somebody said 0.5. 0.5 is the same thing as 1/2. So we're here. This was just technically you could have gone here to there, straight from there to there by plugging it into your calculator. On the right is I showed the work, showed the details. You could go straight from there. Now, one last technique is left is just take sine inverse of both sides. But I wanted to look at this first slide. You can't think intuitively first. So, which is inverse, which are basically talking about in this first paragraph. They say, which angles of B have sine B to equal 1/2? So here they're talking about the unit circle working backwards. There are two angles smaller than 180. There are 30 and 150. So sine B is equal 1/2. So that, to avoid any confusion, since we didn't do 6.4, 6.4 though, it was only about 10 slides of content. 6.4, the whole main idea is solving for an angle and this last step that we're here, because we're trying to solve for angle B. This was not 12, it was 1/2. This was 1/2. The whole idea in 6.4 was that we can actually solve for these angles on this last step that we're here by using inverse trig that we saw in 5.5. So let me give myself a little bit of space here. So 6.4, the whole idea was that when you're down to this last step, you can actually use sine inverse on both sides. If you do sine inverse on one side of the equation, you have to do it to the other. Now it's the same thing as arc sine. They might write arc sine on Newton, which I see they do. Here you would have to do sine inverse or arc sine inverse of 1/2. This would cancel out, and then you're left with B approximately, we'll round to the nearest whole angle, which should give you a nice whole angle. If you do sine inverse of 1/2, what does that give us? Remember, 30. So remember, you would have to be in degree mode. So B, it's not an approximation because it actually equals 30 degrees. So this is from 6.4. This part, that's all from 6.4, that you can actually do sine inverse to cancel a sine and solve for an angle, or cosine inverse or tangent inverse, depending on what you have, what you're working with. But in this case, law of sines and cosines. So inverse sine or inverse cosine. So we get 30 degrees. 30 degrees is our answer. All right, I think they wanted us to find angle B. So we found angle B, and we can simply find angle C. All right, now what they're saying here on the next slide, slide 22, goes back to what I was saying when we first talked about inverse. It says before, when I talked about inverse, I talked about inverse because here we have sine inverse of 1/2. So when we talked about sine inverse or inverse trig, I talked about for what angle in the unit circle would give me 1/2. Sine of what would give me 1/2? Remember, inverse was working backwards because inverse swaps out the domain for the range and range for the domain. So remember, sine inverse, we work backwards. So we go sine of what angle would give me 1/2. Let's see if I can pull up the unit circle. I think I have it saved. All right, so they're talking about sine of what angle would give me 1/2, and I see 1/2 is positive right there. We'll not cover that too. It's positive there, and it's positive there, and it's for an angle of 30 degrees and 150 degrees. Now remember, the total sum of a triangle is 150 degrees. So what the textbook is trying to tell us is there was two possible answers they could fit. Because you can follow me, I believe if you do sine of 150 degrees, you should still get 1/2, right? Can someone confirm that with me? Either by a Y or N, yes or no? Yes, right? So you do get the same thing, and it's true. So sine of 150 degrees is 1/2, but B cannot equal 150 degrees because they gave us some information before about the triangle. They said that angle A was 45. So if B happens to be 150 degrees, we're going to overpass the 180. That's what they're trying to illustrate here. So it says for what angles B have sine B equal 1/2, and we see that from the unit circle. It can be either 30 degrees or 150. But if we chose 150 degrees, we're gonna go over 180 degrees, obviously, right? Because 150 plus angle A, which was 45, will be over 180. And I think they say that as well in the PowerPoint. So there's two possible angles that would satisfy our answer, but the only one that makes sense is 30 degrees. All right, but if you do sine inverse on your calculator, sine inverse of 1/2, it should give you 30 degrees. So which of these angles is compatible? Which of these angles is compatible with what we know about triangle ABC? Which is 30 degrees. 30 degrees is the only one that it's compatible, because if we chose 150, 45 plus 150 would be over 180. So angle B was 30 degrees. And if you want to solve for angle C, just add 30 plus 45, 180 minus that. And angle C is equal to 180 degrees minus the sum of the other two angles, which gives me 105 degrees. 105 degrees. All right, not so bad. Not so bad. Do they want us to solve anything else here? Yes. So if they say solve all parts of a triangle, they're asking us to find all 6 parts, 3 angles, 3 sides. All right. So looks like we know all 3 angles. Looks like we know 2 sides now, do we? Right, because this was a side angle. All right, so we know this to be, we found angle B earlier. I can fill this in. B was 30 degrees. And then C was our largest angle. C was our largest angle of 105 degrees. So now the only thing that it's missing that looks like 105. All right. So the only thing is missing now is little c. The only thing now is missing is little c. So I think that's what they're going to want us to do next, solve for little c. So now that we have all of A and all of B, you can use either A, sine of A over little a to equal sine of C over little c, or sine of B over little b is equal to sine of C over little c. So either case works, either case would work because they're proportional. So let's take a look. Let's finish this problem off, right? So here is the formula for side C. If you want the formula for side C, it's right here. They did the manipulation for us already. All right. So first step was stating the law of sines. Here they decided to use angle B and side B. Again, you could have used angle A and side A. It should give you the same exact thing. But we still need to use sine C and little c because we're trying to figure out that last side, I believe so. So there's our formula for little c. And then we have to just plug in. So little b was 7, right? 7. Little b was 7. Angle B, we got to be 30, right? 30. Oh, where's that? 30 degrees. And then little b, we found little b. No, we don't need little b. I already gave little b. Little b, angle B, and angle C. Angle C was 105 degrees. So, angle C was 105 degrees. All right, so let's go ahead and plug in chug, right? So we have our formula. Let's just go ahead and plug in. B was little c. Here we have sine of 105 degrees. 105 degrees right here. All over sine of 30 degrees. 30 degrees. And then let's go ahead and round to, you could, simplify a little bit more, but sine of 105 degrees. It's not one of those special angles. So we will have to plug into a calculator because we can evaluate sine of 30 degrees, which is 1/2. But sine of 105, unfortunately, it's not a special angle. So from here, let's go ahead and just plug in. And we'll approximate, let's go ahead and approximate to 1 decimal point. So I'm not too sure they gave us any unit of measurement, whether inches. No, they did not. They did not give us any unit of measurement, so we'll just leave it as a regular number. So plugging this in, approximating to 1 decimal point, looks like we get somebody, thank you, Tomas. We got 13.5. Anybody else can second that? Or I guess third that? All right. All right, perfect. So we got more than a few people getting a 13.5. So it looks like it's working. All right, perfect. So far so good. How is this section? Besides the manipulating, seems a little straightforward. Similar from 6.1, 2, and 3, but for non-right triangles. So we have about 10 minutes left. And then I guess we can wrap it up. We have, I think, one more example left, 1 or 2 more examples, which obviously we will not be able to finish in 10 minutes. But again, this is wrapping up. What I was saying, that it may seem pretty easy to some of you. Those of you that have questions, you can email me or ask me after class, or email if there's still people around. If you don't want to ask in front of anybody, email is, we can Zoom and ask questions or email back to each other. It doesn't matter. If there's a will, there's a way we were going to be able to communicate. So in the previous example, we saw from the unit circle, if you plugged it in the calculator, it gave you 30 degrees. But intuitively, let's say we were just doing everything by hand for some problems, right? We would need a calculator. Obviously, in the previous one, we needed 13.5. But in the previous example, when we solved for angle B, there were 2 possibilities, and one of these was not compatible with the rest of the information. So that's why they bold in red, or they have in red. In general, if sine of some angle is less than 1, we must check the angle and its supplement as possibilities, because any angle smaller than 180 can be in the triangle. So to decide whether the possibility works, we can just check by seeing if they add up to what. See if you add them up, do they exceed 180? So we're continuing on. Was this part of the ambiguous case? Yes. So the next example is that case where we have a bisector, right? Splitting our triangle now to forming one triangle into 2 triangles inside. So they say it can happen, as in we see in figure 6. This was the third figure we saw from the ambiguous case. So that both possibilities are compatible with the given information. So in that case, 2 different triangles are the solution to the problem. So we'll start Wednesday, and we're not going to have enough time to finish this one. If I go really fast on this problem, I might confuse you. But it's been fairly okay, this section. So when we do this one, we'll start on Wednesday with this one. I believe we just need to wrap up this one and then see. Is it in 6.5? Okay, this is another example. Yeah, so there's 2 examples. We just need to wrap up this example, and then we see a no solution example. All right. 2 more examples. So, all right. So on Wednesday, we'll see the example of 2 triangles, and then we'll see the example of no solution. Right? They talked about a triangle with a no solution, and then from there we'll transition into law of cosine. So hopefully we get to finish law of cosines on Wednesday. Like I mentioned, it's a little bit shorter. What I remember, a little bit shorter. Formula may seem a little bit. The formula is a little bit longer, but at the end of the day, it's just a plug and chug type of formula. So you have the numbers, and you just plug into the formula, and either round to the correct amount of decimal points asked. So all right. So we'll end up here on in slide 25. We'll start on slide 25, and we are done for today. So looks like we'll be able to knock out law of sines and cosines this week, and then we can start proving some trig identities next week. Awesome. Awesome. So other than that, we are done for today. We don't have enough time to talk about both examples. The example with two triangles and the no solution case. So other than that, we are done for today. We're going to start here on slide 25 or slide 26. All right. Questions, comments, concerns, worries? They're quiet today. Monday. Cases of Mondays. That's okay. That's okay. Alrighty. So we're almost done with chapter 6. We'll definitely be able to finish it this week and then move into chapter 7. And the next exam is going to be after chapter 7. It may seem a little bit quick, but chapter 7, there are some parts that seem a little lengthy. There might be some sections that may take more than one day. A lot of formulas. Besides the proving, a lot of formulas in chapter 7. A lot of formulas. So bear with me when we get to chapter 7. It may seem a little bit more challenging than chapter 6. So if just giving a heads up. So exam 2 will be after chapter 7. So it will include chapter 7 along with the two the two sections from chapter 6, and then exam 3 will be chapter 8 and chapter 9. Midterm. I mean, I really don't know what the definition of a midterm is. I only have had that for one class. Do you mean midterm as like one exam and in the final? That's always what I assumed the midterm was. So I don't know your definition of midterm. So my definition of a midterm is no, we're not having a midterm. So that's why we have 3 exams. So my definition of a midterm, which I've only had one class that was like that on my undergraduate, was one exam halfway in the semester and in the final. Those classes are kind of hard. Those are harder classes because you have one exam that pretty much judges you the whole semester until you take that final. So those classes are a little bit. I don't want to say hard. That was not a hard class. It's just you need to pay more attention to those courses. Because there's going to be so much content. That's why I don't agree with having one exam and then the final, because that midterm is going to have a lot of content on that midterm. So no midterm. If you like, you can call each exam a midterm if you want. Midterm 1, midterm 2, midterm 3 if you want, but no midterm. 3 exams and a final. Any other questions? That's a good question, though. That's a good question to be aware of that, because midterms are very, very critical. Very critical. Yes, the final is going to be after all over. It's going to be all over. It's comprehensive. It's going to be overall the chapters. But again, we'll review. I won't leave you in the dark. We're definitely going to review for exam 2, exam 3, and the final exam. So. Any other questions, comments, concerns? So I can open up those of you who are ready, for some homework. I can open up the homework for 6 point or the homework over law of science. I can open up for 6.5. So be on the lookout for that for today. Homework over 6.5 and 6.6, but we haven't started 6.6 yet. So be on the lookout for that. Other than that, um, we're done for today. I'm going to go ahead and end this meeting just so it can convert. I have not figured out how Zoom can convert a video while you're still in the meeting. I know I can stop recording, but it won't convert the recording into a video until I end the meeting. So any questions, comments, concerns before I end the meeting, just so it can convert. And then I have class. We'll have another class in 15 minutes. College algebra is next. Other than that, we are done for today. We'll see you on Wednesday. Keep up with your homework. Don't fall behind. All right. Everybody have a great day. Be safe. We'll see you Wednesday. I'll be right back. ECHS. If you want to join back in, I'll be right back.